Okay, but let's talk about the second one, which is a big topic in itself. But then, obviously, this textbook just talk about it very briefly. Mhm. That's really well because we don't have time. Otherwise, this is a really nice topic, and I would suggest you to look up online because the figure in the textbook is not it's very straightforward, it's very simple. But if you look at more online information, you can easily search like using a picture search the example of conformal mapping. You see a lot of beautiful pictures. So, con, so transforming from one one complex point to another complex point, and the all these some really striking features. So, and then it has lots of applications. Some of them beyond us, even uh, what you call high energy physics or string theory and that kind of thing. So that kind of there's lots of application beyond us, but there's some application that is closer to what we do, like the finding solution of the Laplace equation. And so that's one of the major applications. But let's talk about this, why we call it the conformal mapping. So the idea is, so all the things that we consider a function of a complex variable, right? So you already mentioned that you can, I mean, very early you can write in real and imaginary part, you have u and v, right? In terms of the x and y at the real and imaginary part of C, right? That's what we do. Right? That's that's the complex function. Sometimes when we talk about uh, complex variable or of conformal mapping, we name it like W. It doesn't matter what you call F or W. But later the example of in this section use W. But anyway, it's the same thing. So basically, the idea is that original the complex plane is Z plane. So the real imaginary part X and Y, right? Then any points on the complex plane like Z, right? And you can evaluate this function W and find the point corresponding points on the plane. The new complex plane is the W plane. It's W plane. Now W has a real part as U and imaginary part as V. And U is here, V is here. Right? So you just evaluate the function and find what U and V's are, and then right, just draw, just find the corresponding point. This is W Z, right? Z and here W is Z. Okay, so that we can map. So map a point, map to another point. That's called mapping. Yeah, U and V. Okay, this is real part is U, imaginary part is V. Okay, yeah, and then obviously you can do it not just for one point. You can do it a bunch of points and find the corresponding point on the W plane for any point on the Z plane. In particular, say a line on a curve or a curve. Or you look at locally, of course, any curve becomes and the smooth curve becomes a line. But, so a curve in the Z plane will map to the curve on the W plane, especially if W map to C map to W in this case, and then there's a curve. Let's draw something close to any closed become a straight line, right? So this curve will map to this portion of a straight line will map to a portion of straight line on the W plane that is also close to W. Z map to W. This line will map to obviously by continuity because all these functions are assumed to be continuous. The analytic function, right? We're talking about analytic function. So map to straight lines, right? Okay, so if you call these points on the on this straight line, give it a name, so whatever. Maybe we'll because this is Z, right? This is W. Let's call this Z equals C sub 0. This point is C sub 0. This is evaluate W as C sub 0, call it W sub 0. Okay. Z sub 0 map to W sub 0. And this line, you can say, you can give an equation of that. Close to Z0, this is a line to Z minus Z sub 0, which has a magnitude and then a phase, right? And in this case, because it's a straight line, this phase is a constant along the straight line. And now then you can figure out what the equation would be for this straight line after you map to the W plane. And what you do is just straightforward. So W. So this is like taking a Taylor series. So this point is W sub 0, right? So W. So all this line is W. W equals Taylor series is the 0 order is W sub 0. You can move it to the other side. W minus W sub 0 is equals to the function. So is the derivative in this case df dz, or you can say dw dz doesn't dz, and evaluate at W sub 0 multiplied by Z. And then you write it in the polar form. So this is theta, right? So it is the polar angle on the W plane. So give it another name, theta or phi. Okay. Right. You write it in polar form, right? This is the W minus W sub 0 e to the I phi equals to now the df/dz is also a complex number. df dz z sub at these two lines at evaluate W sub 0, magnitude of that, right? And then the phase angle of that, which combined with the phase angle of this one, the z minus c sub 0 is e to the I theta. But the phase angle of that, you can call that like alpha. But the alpha is the polar angle of this object, the derivative df/dz. The df/dz has a magnitude of this one, and then the phase angle alpha. Right. So what you see is that this line is mapped from the original line. They changed two things. One, the magnitude change from z minus c. Originally, z minus c sub 0, the magnitude. But now you multiply by the magnitude of the derivative. So that's either magnify or shrink, or whether it becomes larger. It depends on whether df/dz is greater or smaller than 1, right? Whether it's throwing it up or just shortening this length, right? But another effect is this alpha. So this alpha is the phase angle of the derivative. So basically, this line is rotated by a alpha. Say in this case, theta is, we draw the theta here. This would be a theta. This would be an alpha. So this line originally has an angle theta. Now after you map to the W plane, it add the angle alpha. That is the phase angle of the derivative. So, so the mapping has the effect of changing the scale. This is basically the scale factor, and then rotate it. For any localized around any localized point, it change the scale and rotate it. Okay, and you can see that this is considered one line, but any line, any theta will work the same way. So we draw. This is line one. You can draw a second line two, right? And then the same thing applies. So whatever this angle is equal to that pi over 2, but doesn't matter. It's still at the same alpha. So when you transform to here, so basically whatever the original theta, we move an additional alpha in this case. This will be second line. So it rotate together. So whatever the angle between 1 and 2, obviously they will maintain the same angle after you map to the W plane, right? So whatever this angle 1 and 2, so basically these two lines will rotate together. Right? 1 and 2 will, whatever the alpha will rotate a little bit and go to the W plane, right? And you can see that this will apply to any angle, and then all the angle will be preserved after the mapping. So that's we call it the conformal mapping. Conformal mapping basically is saying the angle. This mapping will preserve the angle between lines. So that's have a nice property. You map a realistic objects, even like the face of a person. You draw a face of a person here, map to that on the Z plane, and then you map to the W plane. First, that will have some scale change, but then you can still recognize it's the same person because all the angle between the face, all the angle between the IA lines and the nose and all that will be served. So that's no distortion, right? At least locally, of course, if you go further away, that would be further distortion. But if you stay locally, when the theta expansion still apply, they preserve the shape of that object. Okay, and that is one good thing about this. You can see that obviously that many applications like doing visualization. Yeah, any curve, say you map, say you have a curve like that, right? So you have a locally I didn't draw it, but locally it's a square. So all the angles are pi over 2. When you map to the W plane, it will still be something like all the right angle will preserve all the angle between any two lines will be preserved. Obviously, there are exceptions. There are two exceptions in this analysis. First, this doesn't apply if the FTC is 0. Obviously, if it is 0, then this term is 0. Then you need a high order term, right? High order term, which we ignore. If the first order term is 0, then this doesn't apply. And you can see that if it is second order, then there will be a d z minus c0 square, right? So the angle phase angle will actually multiply by 2 first. So that phase angle will multiply by 2. But that's only around the point that the derivative is 0, right? Derivative is 0 is still identical, which is fine. So, but the second case is when derivative is not 0 or is not analytic or singular. So usually the case is the derivative goes to infinity. So this magnify the scaling factor magnification is goes to infinity. So it's magnifying to infinity. So usually that say any point will map to infinity. You go to far away from the origin on the W plane, which is fine. Sometimes we'll use a mapping or function f that has a singularity, which sometimes is important because the next application we talk about is that sometimes we want to map a more complicated curve to a simpler curve. Like in this case, if you want to map like a oval or whatever closed curve, you want to simplify it on another plane. In a double plane, say if you want to go through, just map it to a straight line, which is in many cases possible. Map this curve to a straight line. You want to do a mapping, something like that. And obviously, on the W plane, a straight line will go to infinity, right? So if this curve will map to a straight line, which will go in the positive or negative infinity, it doesn't have to be on along the axis or imaginary axis. It can be any arbitrary point, but it still goes to infinity. So, which means in this case, this curve must encounter one of the poles of the mapping function, right? Because when you hit the pole by this consideration, dft is equals to infinity, you map this to infinity, right? So this curve, if this curve map to a straight line, then somewhere, so this part will approach this pole, then we will approach the plus or minus infinity. Okay, so sometimes the application was for a mapping that has an isolated singularity. You see that in homework form. Okay. Yeah, okay, so that's the meaning of conformal mapping. Yeah. Question.
Yes, and you know that this theta is the argument.
Yeah.
So does it only apply for the principal argument or also the argument? Because
this theta is the polar angle of this quantity c minus c sub c. Yeah. Yeah.
So when you're comparing, you are mapping.
Yeah.
Because I see theta here. So this theta is 2 theta. So that the other angles get affected or the other angle that
well, if you just have the linear term, obviously this formula apply. If what I'm saying is if dfdc is 0, then you drop this term. You have definitely you don't have this, and then you have second order derivative. Right? Then you have a second order. So you have 1 half d square fdc square, and then you have c minus c sub c square e to the 2I theta, and then plus the whatever the phase angle of this second derivative, whatever you call beta. So that in that case you have two phases. It's not like this originally. So every angle you need to multiply by 2 before you rotate by this beta. So obviously that would be different. So imagine you have a line that is zero along the horizontal ones, and theta is 0, then 2 theta is still 0. Then this line is just rotated by this beta. But for another finite angle, you multiply by a factor of 2 first before you add the beta. So obviously the angle does not preserve. Okay, so that case is when DFDC is. So this is not a singularity, but when you map to a mapping, that becomes a singular point. Right? Okay, is it what you asked for? Okay. Yeah. All right.